Hello everybody and welcome back to another video. We've got quite a bit of wet weather here at the moment, so I can't be outside working on the boat. The boat's actually full of water at the moment. I went to it yesterday and I sort of bucketed a heap of water out of it because I've got no electrics on it at the moment, because I've gutted the whole boat. I've torn all of the electrical systems out of the boat, and I need to replace it all. So at some stage I'm going to have to very quickly put a bilge pump system in there, so when it does rain like this, then I can pump it out. But anyway, what I want to have a look at is basically I'm going to start concentrating on a lot of the electrical systems and the electrical design, why we do certain things and what's really important. So what I've done is I've set up 3 different cables in exactly the same length, and what I want to do is basically look at the voltage drop and work out why it's very, very important to get our cable sizes right, or at the very least make sure that we've got the minimum overall size of the cable that we need for a certain load. So the load I'm talking about, whether it's a bilge pump or a kettle. I'm going to use a kettle here as it for this example because that draws 10 amps. It's a pretty good example. Any device whatsoever. So essentially what we're going to do is we're going to measure the voltages at the source, so at the battery itself, and then we're going to measure the voltage here just before it goes into the kettle, and then we can have a look at the voltage drop and work out whether a cable is suitable for that particular appliance or not. Now I've got 3 cables here. I've got a 6mm squared tin copper cable, so that's a decent size there, pretty big. Well, it's not really, it's probably in the small size. Some of the cables that I'm going to be using on this boat are up to 75mm squared, 32mm squared, some of them going to my winch. I've got a big drum winch on the front of the boat, so that's a decent sized cable. And then we've got this one here, which is must state it here somewhere, 0.44mm squared. So this is typically, that's only a copper wire. That's a 2 pair, so you've got 2 pairs. Normally we use these on security systems in buildings. So what we've got is the black and the red would normally be supplying the power to a passive infrared detector or something like that. And then we've got just a blue and white pair. So all I've got connected up on this system at the moment is the black and the red to supply our power. So that's 0.44mm squared. That's pretty small. And then we've got another one, and it's somewhere in between, and it's 1.13 squared. So there you go. It's somewhere in between, a little bit bigger than that 0.44, just over twice the size of it. It's a tin copper cable as well, so single pair, PVC insulated, PVC. So when we talk about PVC, we're talking about the outer insulation here to protect the conductors from any sort of mechanical damage, and then we've got the PVC insulation to stop them both from shorting together. Alright, so let's see what we get. Let's see what sort of findings we have. What I'll do is I'll turn it on at the very beginning, and I'll have a look at it with no load on whatsoever, and then we'll compare it to what happens when we put a load on. And I just want to do this in this sort of format to see if it hopefully makes some sense to you. After doing this for 40 odd years, and it's sort of second nature to me, but there's a lot of people who might struggle with understanding the process and how to measure things and what it all means. So I want to do it in a practical way, not just, they just want to do it in a practical way, guys, and see if I can find ways to do that. So I've connected up the kettle at the moment. It's connected here, just through those 2 wires there. I've had to put a knot in the wire because I had to differentiate between the positive and negative on this particular wire because it's not color coded or anything, so that's why I've done that. So what we're going to do is turn it on. So I'm just going to flick this circuit breaker over here. The kettle is now on. I haven't got my lead connected, so I'll connect my lead up. Remembering this is the larger cable, so we've got 12.85 volts on there at the moment. Alright, 12.85 volts, And at the supply here, I've just got a dodgy old alligator clip there, 12.99. Wow, that's a bit of a voltage drop for such a small load. But anyway, we won't even worry ourselves about that at the moment. 12.65 volts. 12.65, I'll write that down. Here's a little bit of a helping hand for you too, guys. Whenever we use insulation tape, we normally always use white insulation tape. The reason for that is basically when we're marking our cables, we're running cables through buildings or wherever we're running our cables, we need to mark them so that we know which one's which and everything. Sometimes we'll just write it on the sheath of the cable, but other times we'll write it on the insulation that we've wrapped around the cable. So what we've got is 6mm squared. Our source, our voltage here at the load was 12.65 volts. We're going to measure the current at the moment. We're going to put that there, and we're going to put our source voltage. Alright, so now we're going to measure the current using this clamp meter. So I'll turn it on. I'm going to put it on to 40 amps DC. You'll see that properly. And I've got to hit this little button down here, this little REL button. Not sure what it means. I believe it's relative. So we hit that and you'll see it zeroes itself out, because prior to that we had some sort of residual current flowing through it. We put him up here. Oh, on the wrong wire. I've disconnected that one. Wondering why it's got no current. So we put it on there and we should have, oh there you go, 11 amps. Okay, so we've got 11 amps currently flowing through our cable that is a 6mm squared. Alright, put that down. Okay, so what I've done now is I've moved the kettle up to the second wire, which is the 1.2mm squared. Let's just call it 1.2mm squared. And I've connected my multimeter up. I haven't got it turned on at the moment, so I've got 0 volts DC there. And we're going to turn it on. So I'll turn it on now. Let's have a look at what we get. 12.3 volts. So the first thing to notice is our original voltage on the 6mm square cable was 12.65 volts. So we've now got an additional 0.3 of a voltage drop across that smaller wire. Our current is now 10.19 amps. So why is that? Now I don't think we're going to be able to feel it. So in basic terms, what we've got now is we've got a greater voltage drop, 0.3 of a volt. We've got a lower current. Remember, I haven't gone through this yet, but when we have a look at Ohm's law, this will probably make a little bit more sense. So essentially, the smaller wire has meant that we've got less voltage at our source. If that's you know, our lights or something else, it's not quite at that point where it's going to become a huge issue yet, but it can create problems like lights flickering or your depth sounder or your GPS starting to drop off and get dirty power. That's what we mean by dirty power as well, is when the power supply to the device is fluctuating or moving, or you've got noise on it or anything else, then that's considered dirty power. So that's significant. That's a fair bit anyway. So let's move it up again to our smaller wire. So this thing's only 0.5mm squared. It's a tiny little wire. So basically that's the third one and the smallest wire connected up, that tiny little 0.44mm wire. See if there's any heat generated in that yet. No, I can't feel any heat in that just yet. It's dropped down to 11.2625 volts. So when we have a look at our 3 different cables and what we measured on each of them, let's have a look. So the very first one we did was the largest one. So marked up here, it was a 6mm squared cable. Our voltage at the source was 12.94 volts. Our voltage at the thingamajig, the load, the voltage at the load was 12.65 volts. and it was drawing 11 amps. Our system test with the 1.2 millimeter squared cable, our supply voltage was 13.12 volts. I might have to do this one again, I'll double check that. Our voltage at the load was 12.26 volts and the current was 10.12 amps. Alright, 0.44 we got 13.15, 11.33 at the load and 8.12 amps. Okay, so we've done the test, so that's all well and good. We know that we've got those voltages and the current measurements that we got there. We got 11 amps at the thicker wire, the 6 millimeter squared wire, and it was only drawing 8.21 amps on the thinner 0.44 millimeter squared cable. Why is that? Well, I sort of mentioned before, I haven't gone into Ohm's law yet, but we will talk about that probably in some depth at sometime later, because sometimes that sort of stuff it's done by everybody talks about it, and there's plenty of videos out there showing that, but I'm trying to make things as practical as possible. The thing that we need to keep in mind is we can see the voltage drop, we can see the current's gone down with it, and we know that at the end of our wire we don't have enough supply to our kettle. Our kettle's no longer working efficiently. It's a 150 watt kettle. It should be drawing, you know, anywhere between 11 and 12 amps, and it's just not achieving that. So what does that tell us? Our first voltage was 12.65. This is at the source itself, okay, minus 11.33. So the overall voltage drop between the two is 1.32 volts. Now that might not seem a lot, but when we have a look at the current, that's a bit different. We've got 11 amps minus 8.21. So that current, so that's essentially drawing less current. It's drawing 2.79 amps less than what it was on the larger wire, or the larger cable. Okay, so we've proven the fact that we've got a voltage drop and our current has gone down significantly over, you know, the course of this test. Just testing those 3 different wires, and that's very small load considering that kettle there's 12 volt DC 150 watt kettle was drawing 11 amps and it dropped down to 8.21 amps. The reason it's dropped down to 8.21 amps is essentially because as that voltage has dropped, the resistance increases, and that's the part of Ohm's law, something that we'll potentially have a look at later. But the important thing to take into consideration is as that cable heats up, the resistance increases. As the resistance increases, the current drops. That'd be a good thing, you say. There's less current and less chance of heating up. No, because what it does is it starts to heat up a little bit more, current goes down a little bit more, heats up even more, current goes down even more. And the problem that creates is, 1, you've got a hot wire or cable system, and 2, you've got a load that's trying to operate at less than operating voltages. So you've got you might have multiple devices hooked up to the same system, to the same cable on a spurred network or a sub-circuit of some sort. So what's happening is some of those devices are going to start to flutter and fluctuate, or lights are going to start to flicker. Your GPS might drop out and go, oh no, I can't handle this, and go, turn itself off. Your winch might start to fade. So lots of different things to consider there. Voltage drop is very, very important. It's you know, it's very, very important to have clean power to, especially to critical circuits. So critical circuits, I think we'll talk about in another video, but very, very important. So the critical circuits being our obviously critical systems within the boat. It might be the GPS, the compass. If you've got a compass with a backlight on it, it might be your bilge pumps. Big one, bilge pumps. You don't want water building up in your boat. You want them to continue working. If the voltage gets too low, they might stop working. Very, very important. So that's why we've done this little test. I hope that all made some sense to you, and I look forward to doing some more, and I'm trying to keep them as practical as I possibly can, so that you can see how we do the measurements and how it relates. In this particular scenario, we saw the difference between, you know, our voltages from the larger, thicker cable to the smaller, thinner cable, how that was affected. Our overall current, how our current changed. It started at 11 amps and then dropped right off. So very, very important. Cheers guys, and I'll catch you on the next one.